OK, so at this point, we have seen one-time pads and how they work and why they are impractical. So we need to go searching for something that computers can actually implement that don't have the problems that one-time pads do. As a reminder, we're still in the top left square. So we're still doing symmetric key schemes that provide confidentiality. But we are throwing away one-time pads and trying something a little bit different this time. So we're going to try to design something called a block cipher. So let me give you the definition, and then we'll talk about why it's useful. So the block cipher looks like this. It's kind of like all the other encryption schemes you've seen so far. It takes in two arguments, a key, there's K, and a message, there's M. And it outputs some string. That's the ciphertext. And the way that this function is implemented, for now, think of it like drawing arrows on a grid. So the way that I would define this function is I would write out all the possible messages and all the possible ciphertexts. And then I would draw arrows showing which plaintext maps to which ciphertext. So for example, if I want to encrypt 0, 1, this arrow tells me that it encrypts to 0, 0. And if I want to encrypt the bit string 1, 0, this arrow tells me that the corresponding ciphertext is 1, 1. So the way that I think about this, and the reason why I've put this K as a little subscript here, is I think of block ciphers as a family of functions. So in reality, you can think of it two different ways. You can think of it as a function that takes in two arguments, a key and a message, and it outputs some ciphertext, just like any other encryption scheme that we've seen. But another useful way to think about block ciphers is think of it like a family of functions. It's a one big family, and there's lots of different pictures that all look like this, where there's arrows mapping inputs to outputs. And the way that you pick one exact function out of the big family is you fix K. That's why it's a subscript. So as soon as you pick K, you have committed yourself to one of many possible functions in this family. So let's say you go here and you set this equal to 1. Alice and Bob are using the key 1. So then what that means is, in that big family of functions, pick out the first one. And maybe the first one looks like this. It maps 0, 0 to 0, 1, and 1, 1 to 1, 0, and so on and so forth. For every possible message, this particular function tells you the corresponding output. That's why people call it a permutation. For each input, you get one of the outputs. So that's how I think of this. It's a big family of functions. If I wrote out all of the possible E sub k of m, I would get this diagram repeated once for every single key. But as soon as you pick one key, like you say k is equal to 2, then what happens is all the other possibilities disappear, and you're just left with one of these pictures, right? Because if k is fixed to 2, then there's only one input. That's the message. That's this stuff right here. And there's one output. That's the ciphertext. So as soon as you pick a k, all the other permutations are discarded, and you've committed yourself to using 1. And because you've already fixed k, this is a function with one input, the message, and one output, the ciphertext, and the arrows tell you which one is which. That's what a block cipher is. It's a big family of functions, all under the name E. But once you pick a k, it narrows down to 1. And the way I draw it is with a bunch of arrows. So now that we know what the block cipher is, we should ask ourselves whether or not it's correct. So turns out some block ciphers are correct, some are not. It depends on how you implement E and how you draw these arrows. So let me give you one example of a block cipher that works and one that doesn't work. So this block cipher on the left would not be valid. So if this was E sub 5 of m or something, that particular E is not going to work. This is a block cipher that doesn't work. And to see why, let's say you encrypt 1, 0. So then what you should do is you should follow the arrow. You get 1, 1. And now let's say Bob needs to decrypt the message. So Bob knows the key. And so because he knows the key, he knows which one of these diagrams we're using. We're using this one. Remember, there's a big family of them. If Alice and Bob know that k is 5, we must be using this particular one. So Bob knows this picture. And he receives the message 1, 1. And he has to decrypt it. But what does 1, 1 decrypt to, according to this picture? Does it decrypt to 1, 0? Does it decrypt to 1, 1? It's not so clear. Both of those would be valid choices. So in this picture, this particular block cipher doesn't work because when Bob receives 1, 1, it is not clear if it decrypts to 1, 0 or 1, 1. both would be valid plain texts. So what we call this is a function that's not bijective. There are two inputs that encode to the same output. The arrows point at the same output. And it's impossible to go backwards to a unique input. So this is a case where Bob is not able to uniquely decode. So when we build block ciphers, we have to be very careful to not draw any pictures that look like this. It will not work. By contrast, here is a bijective permutation that does work, because every arrow points to exactly one output. So now if Bob receives 1, 1, he can uniquely decrypt it back to 1, 0. Or if he receives 1, 0, he can uniquely decrypt it back to 1, 1. So the one on the right is what we want. And a valid block cipher should be designed so that every possible mapping, the one for k equals 1, the one for k equals 2, the one for k equals 1,000, all of them should be pictures that look like this. And one final thing I should mention is block ciphers are defined on a fixed input length. So here I set n equals 2. That's why each of these pictures has 2-bit inputs and 2-bit outputs. And if n was, say, 30, you'd have to draw 2 to the 30 inputs, 2 to the 30 outputs, and map them for every possible key. So that's what a block cipher is. It's a big family of functions, one for every key. Once you pick a key, you narrow it down to one particular diagram, and that diagram shows you all of the m-bit inputs, all of the m-bit outputs with arrows between them, and hopefully the arrows are bijective. And one final thing I should mention is that in reality, when you design these things, because someone has to write the code for E, you don't actually write out these arrows. You'd write a piece of code that generates these arrows for each key. But I think intuitively, thinking about the arrows can help you a little bit. But do know that in real life, no one is writing out 2 to the 30 columns in a big table. What they're actually doing is writing a piece of code that can be used to generate those tables on demand. OK, here again is the block cipher definition, but with a little bit more math. So once again, we see the encryption function. It's a piece of code that someone writes. It takes in an n-bit plaintext and a k-bit key, and it outputs an n-bit ciphertext, where n and k are both fixed values that you decide ahead of time. So just like our other encryption schemes, it takes in plaintext, key, outputs a ciphertext. The lengths are all fixed. And the decryption function does what we expect. It's a piece of code that someone writes, takes in a ciphertext and a key, and it outputs the corresponding plaintext. And if you open up the E or you open up the D and you look inside, it's really a piece of code. But what I think about that code doing is you can think of this little box holding all of those tables with arrows showing how each n-bit input maps to an n-bit output. There's one table for every key. And as soon as you fix a key and you say Alice and Bob are using key number 12, and they're using key number 12 forever, you've narrowed it down to that one particular mapping. A little bit of math that you might see sometimes. This is just notation that says k-bit input, m-bit input, and m-bit output. Not the most important thing here, but sometimes you see that. So some properties of block ciphers that are hopefully correct. One is correctness. And as we talked about before, correctness means that the encryption function needs to be a permutation. Each arrow has to point to exactly one output. And this has to be true for all the arrows inside that box. Efficiency, hopefully this thing performs relatively quickly, so people want to use it. And we'll talk about security coming up next. But this is the definition of block ciphers and how they work.